at the integral test, and essentially the integral test allows us to determine whether a series converges or diverges. And it allows us to determine whether a series converges or diverges by converting it into an improper integral. And essentially by looking at this series, a sub n from n equals 1 to infinity can be converted into f of x dx from k, a finite number, to infinity. And this central definition is only works because it is implied that a sub n is equal to the function that is used in the improper integral. In addition, the integral test focuses on testing for divergence or convergence by evaluating the improper integral. And by evaluating the improper integral, you're able to determine whether the improper integral converges or diverges. For example, if the improper integral f of x dx from k to infinity converges, then it is also assumed that the corresponding series a sub n to n equals 1 to infinity converges as well. And this is also for divergence, where the improper integral f of x dx from k to infinity, if that diverges, then the corresponding series diverges as well. The integral test can only be used if the function meets three conditions. First, the function must be positive within the given interval, and that's essentially if you were to graph the function, all of the y values are above the x-axis. The second is that the function is continuous throughout the given interval as well, and this essentially states that there can't be any vertical asymptotes or any types of discontinuity. Lastly is that the function is decreasing throughout the whole interval. And decreasing can be determined through graphing or by plugging in numbers or by using the first derivative test and by finding critical points and determining where it increases or decreases that way too. After the function in the improper integral satisfies these three requirements, you are then able to examine the improper integral. So to begin, the first example is determine whether this series 1 over n squared from n equals 1 to infinity converges or diverges. So by looking at the series, you're able to determine that 1 over n squared is equal to a sub n, and a sub n is equal to the function, or f of n. And thus, you're able to convert this series into the improper integral 1 over x squared from 1 to infinity.
Go.
After you convert the series into an improper integral, you then have to evaluate whether the function satisfies the three conditions. This is the graph for the function 1 over x squared, which was our function. And basically, as you can see from 1 to infinity, it is positive, so it does meet that first requirement. It is continuous from 1 to infinity. It does have a vertical asymptote at x equals 0, but because that's not in our interval, it is still continuous in that interval. Lastly, as you can see, when x approaches infinity, y approaches 0, so that shows that it is also decreasing. After you determine that this function satisfies the three requirements, you can then integrate the improper integral. So to begin, you can't use this improper integral because there is an infinity as the upper bound. So you have to convert it into a limit notation and replace this infinity with a variable. So the limit of a as it approaches infinity with the integral from 1 to a over 1x squared dx. You can then take the antiderivative of this function, which is negative x to the negative 1 power, and evaluate it from 1 to a. After you've taken the antiderivative, you can then evaluate the integral. You plug in a and 1, and you can evaluate the integral. After you plug in a and 1, you can then substitute infinity for a. So it'd be negative 1 over infinity plus 1, which as a result would be simple as 0 plus 1, which equals 1, and thus you can conclude that the improper integral converges. The improper integral equals to a finite number, so therefore it converges. And with the definition we used before, when 1 over x squared dx from 1 to infinity converges, that also implies that the given series, the one that corresponds to this improper integral, converges as well.
Go.
So, by looking at a different example, this question is, determine whether 1 over square root of n from n equals 1 to infinity converges or diverges. So similarly, by looking at the series, we can conclude that this part right here is equal to a sub n, and a sub n is also equal to f of n, the function. So we can convert this series, 1 over square root of n from n equals 1 to infinity, to the improper integral 1 over square root of x dx from 1 to infinity.
2, 1.
Similarly, after we convert the series into an improper integral, we then have to determine whether this function satisfies the 3 requirements. So instead of using a graph, we can plug in numbers this time. And as we plug in 1, 2, 3, and 4, we can see that all 4 of the values are positive. In addition, all 4 of the values are decreasing as x approaches infinity. So this verifies the first and third conditions in that this function is positive and it is decreasing within the given interval. In addition, in order to determine whether this function is continuous in this given interval, we have to determine whether which values it is undefined at. In order for this function to be undefined, the denominator has to equal 0. So square root of x equals 0, and the only values where x can be undefined is at 0. So essentially, this function is continuous because 0 is not in the given intervals, and thus this function does satisfy the first, second, and third requirements. After you have satisfied the 3 requirements, you can then integrate the improper integral. So like before, you have to substitute a variable a with the infinity at the upper bound, and thus use limit notation. Then you can take the antiderivative of this function, which is 2 square root of x, and evaluate it from 1 to a. Then you plug in values a and 1, the upper bound and the lower bound, which would be 2 square root a minus 2 square root 1. And then you're able to plug in infinity because it is a as it approaches infinity. So it would be 2 times square root of infinity minus 2, which is essentially infinity minus 2, which equals infinity. And thus this implies that this improper integral diverges, and thus the corresponding series, the series that was given, diverges as well.